So this one is about the mutual inductance. The mutual inductance. As you can see here, we have a battery, and then we have a big loop, big uh, big coil with radius R1 and another coil R2, which is slightly small, actually smaller. And then here we don't have a battery, so and only we have a sensitive ammeter to measure this current. Well, so this one has a radius of R2, and the turn for the coil 1 is N1, the coil for N2 is for the coil 2 is N2. So derive an expression for the mutual inductance M of this arrangement of these two coils, assuming that R is much larger than R2. R1 is much larger than R2. So that actually we would like to calculate actually we like to calculate phi 21, which is B1, which is the magnetic field generated by this large coil, because here we have a battery. Here we have a battery. So it would generate the B field. And multiply by the area of the coil 2, because we need to consider the magnetic flux for this area rather than the large area. And actually, if this one is changing, then it would generate a changing magnetic flux for this small coil, so that we consider phi 2 1 like this, B1 times A2. So next, we consider that M is N2 phi 21 over I1. Because for a single inductor, we will have L equals N phi B over I. That's the definition of the inductor. So for the mutual inductance, we have a similar expression. So we have a similar expression. So we have N. So we consider the N2, the number of coil for the coil 2, and multiply by this one, and divide by I1 instead of I2, because we have I1 here. So which means that we substitute this one here. So we have M equals to N2 B1 A2 over I1. So actually from equation 29, 26, you can check back in the previous chapter. So BZ would be mu 0 I R squared over 2 R squared plus Z squared to the 3 over 2 power. You can check back that one. So actually this is a magnetic dipole. Magnetic dipole generate a B field. Generate a B field. So it's somehow like we have a magnetic dipole. So it will generate B field in this axis. So this is Z and this is R. This is R. So here suppose these two coils are at the same level, which means that we take Z equal to 0. So we consider Z equals to 0, which means that we just know this one, and it will become mu 0 I this R square to the 3/2 power will be R cube. R cube will cancel 2 order of R, so it becomes something like this, right? So in this case, B1 would be N1 will be B1 will be N1 times mu 0 I1 over 2R1 like this, and then we can substitute it into here. So so maybe I add an additional page here. So we can substitute this blue equation into here, so that we have M equals to N1 mu 0 I1 over 2R1, which is nothing but B1, and then multiply by N2 A2 over I1 because actually we just put B1 in front. We have N2 A2 over I1. So here we have N2 A2 over I1, and this one is the B we got from the 2926. And actually, A2 should be pi R2 square. A2 should be pi R2 square, so that we can have N1 mu 0 I1 over 2R1, and then multiply by N2 pi R2 square over I1. So I1 and I1 can be cancelled. This makes sense because it shouldn't be related to I1, similar to the inductor. For the self-inductance, it is normalized by the current itself. So here, the I1 cancel each other. And finally, it becomes pi mu 0, which are two constants, N1 and 2, R2 square over R1, 2R1. So which is an interesting formula. So these two are constant, we don't need to comment on that. So as long as we have more coils for uh, for both uh, for both coil, more number of coils for both coil 1 and coil 2, then the mutual inductance will be larger. And the larger the second coil is, the mutual inductance will be larger. And smaller the coil 1 is, the mutual inductance. So part B, what is the value of M for N1, N2 equals to 1,200 turns, R2 1.1 centimeter, R1 15 centimeter, 15 centimeter. So actually, R1 is much larger than R2. Is used here. R1 is much larger than R2. Because for this one, we also assume that RZ is much larger than R2. So only R1 is much larger than R2, then we can assume the B field inside this area is constant. Otherwise, the B field inside this area is not necessarily constant. So for part B, we only substitute all the number into here, and then you can find out that I don't repeat it at all. So it is nothing but 2.29 millihenry. You only need to plug in N1, N2 equals 1,210 here. R2, R1 to be 0.0011 meter, and then this one is 0.015 meter, 0.015 meter, and that's it. This is two constant, 3.14. This is 4 pi times 10 to minus 7. So any question regarding to this one? Okay, so next. So a long coaxial cable consists 是同轴那个线，同轴线。Consists of two thin wall concentric conducting cylinder with radii A and B. Okay, this one is A, this one is B. Watch. So the inner cylinder carry the static current I, and the outer cylinder provide the return path for the current. The current sets up a magnetic field between the two cylinders. So for RF signal, it is somehow not like what we consider in circuit analysis. In circuit analysis, we assume the lump circuit equivalent. But for high frequency or if the circuit is in a very large scale, like the power transfer system, then we must consider in EM wave sense. So calculate the energy stored in the magnetic field for length of the cable. So for coaxial cable, we usually try to transmit some sort of high frequency signal as high as megahertz level or even gigahertz level. So we need to consider the EM effect. So in this case, wow. actually, according to the Ampere's law, we know that B dot ds equals mu zero I and we assume the Ampere's loop to be this one. This is the A loop, Ampere's loop, Ampere's loop. So the enclosed current is this one, which is I. So for return path, it means that I may go inside, then I may go outside at the outer cylinder. So they're in opposite direction. It's not necessary. It's not grounded for one of them. The other one is the return path to let the EM wave transmit to let the signal transmit. Yeah. So actually, we will assume that the B field is uniform. Is uniform on this Ampere loop. So for the left hand side is nothing but 2 pi r B equals mu 0 I, so that it comes up with a familiar equation, which is mu 0 I over 2 pi r over 2 pi r. So actually the energy store here is 1 b squared over 2 mu naught. 2 squared over 2 mu naught. So here it is 2 mu naught and then mu 0 square I squared over 4 pi squared r squared. So it turns out to be one of the mu 0 cancelled. So it becomes mu 0 I squared over 8 pi squared r squared. So this is DUB, and this is not the total energy yet. We need to integrate it over the integrate it from A to B. Integrate it from A to B because it is an expression between A and B. If the Ampere loop go inside, then the enclosed current will be 0. Then there will be no magnetic field inside and no magnetic field outside because we have I for the inner loop and negative I for the outer loop, so that they cancel, so that there are no magnetic field outside. The only B field is only stored between A and B, so that when we need to calculate the overall magnetic field, so actually we need to so we actually need to so we need to consider DUB will be UB multiplied by DB. So in a very small volume, we can assume UB to be a constant. And in this case, it would be mu 0 I square over 8 pi square r square, and then dv should be r dr d theta, multiplied by dz. So this is a cylindrical coordinate. Cylindrical coordinate. So this is a polar coordinate, and then we have an independent z-axis for the cylindrical coordinate. So actually UB, the capital UB will be the small ub. And then we can just substitute this one into here. So we will have some constant term mu 0 I square over 8 pi square. So these are the constant term. And then for the dr, we have r square r. So we have 1 over r here. And then we should integrate it from A to B. As I mentioned, there are only magnetic field between the inner radii and the outer radii. So d theta is nothing but 1 from 0 to 2 pi, because it is a whole circle. And dz should be the length. The length of it, the length of it is L. That's the length L of the cable. So it's integrated from 0 to L. So it's nothing but L. So this one is ln b over a. This one is 2 pi. This one is L. So it turns out to be mu 0 I square L, and then 2 pi and 4 pi square. We only have 4 pi left, and then ln b over a. So the expression look like this, which is pretty beautiful. Any questions? So for part B, you're asked to calculate the stored energy per unit length of the cable if A equals to blah 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 B and I. So actually it asks you to calculate the UB over L. UB over L. UB over L would be mu 0 I square over 4 pi ln b over a. We just move this L to the left hand side. Just move the L to the left hand side, and then we plug in all the values. So mu 0 is 4 pi times 10 to minus 7. So we have 4 pi here. So we only have 10 to minus 7, and then 2.7 square ln 3.5 over 1.2. So the answer will be 7.8 times 10 to minus 7 joule over meter, because it is a total energy per unit length. So the SI unit should be joule per meter. Any questions? Okay, so we still have another one. Yeah. So for this one, two parallel loops of wire have a common axis. So which means that as long as you connect the center of these two circles this line is perpendicular to this true coil uh, on that plane, on the plane. Yeah, it's perpendicular to this plane and this plane. So the smaller loop radius r is above the larger loop radius of capital R by a distance. X is much larger than capital R, so they must be far away. And so that we can use this equation, because for this equation we also assume that z which is the x here, which is the x here, is much larger than this r. So consequently, the magnetic field due to the counterclockwise current I in a larger loop is nearly uniform, throughout the smaller loop, because this is much far away and this is small. This is small. Okay, suppose that x is increasing. Of course, it is not actually uniform, but this is just an assumption. This is just so it only tells you that it is nearly uniform, and so that it lets you to assume that this is uniform. Suppose that x is increasing at the constant rate v equals to dx dt. Yeah, suppose x is increasing, which means that this coil is moving upward. This coil is moving upward with a constant speed v equals dx dt. So find an expression of the magnetic flux through the area of small loop as a function of x. So here we make use of this one. And actually we only need to exchange mu0 to pi. Actually, yeah, we change z cube to x cube here, because in this problem we have x rather than z, so we just replace z by x, nothing special. And for mu is the current multiplied by this area, so it is nothing but I pi capital R square. And then the direction, we assume this direction is x-axis, so we have I here. And we assume that the magnetic field is uniform. So we make this approximation. So the magnetic flux is approximately B times A. So B is mu0 I pi R square over 2 pi x cubed, and the A for this one should be pi small r squared. So pi and pi can be cancelled. So it turns out to be mu0 I r square r square. We still have another pi here. So that we have another pi here, and then over to x cubed. So this is the expression. Okay. Yeah. So any questions? Okay, now so next, in the small loop, find an expression for the induced EMF and see the direction of the induced current. The induced current. So it is interesting. So just now we calculate the magnetic flux. The magnetic flux due to the big coil. The big coil. So according to the Faraday's law, E should be negative d phi, d phi d phi b dt. So this is the Faraday's law, and then we substitute this expression phi b. So this expression here, take the derivative. So most of the term are constant. So which is equal to minus pi mu naught I r square over 2. So all these stuff are constant. So pi mu naught I r square 2. Only x cubed is dependent on the time. So we take the derivative of time with respect to 1 over x cubed. Because only this variable change with time. Other are constant to time. So we take this one. So in this case, we have this one, x to the minus 3, x to the minus 3. So take the derivative, it should be minus 3. It should be minus 3x to the 4th power, right? X to the 4th power. So in that case, we have minus sign, and other minus sign, so that they become 1, they become positive. So we have 3 pi mu naught I r square over 2 and then we have x to the 4th power, and don't forget the chain rule. So we take this derivative, and then we need to have the chain rule. We still have dx dt. Right? So we still have a dx dt here, which means it is v. Okay, this is a chain rule. The chain rule. Don't forget that term. Because you can regard it like this. So this is d dt 1 over v. So maybe you can just make it like y equals this one. So we have so this one should be d y dt, and this one should be dy dx dt, somehow like this. So this one is minus d over x to the 4th, and this one is dx dt, which is v. So this is the answer for part B, and for part C, you can imagine that well you can regard it from 2 approach. You can got the idea for the direction of the EMF from 2 approach. One approach is you determine by Lenz's law. Yeah. So if we have have a coil here, and then this is moving away, so that the magnetic flux is decreasing, so that this coil will try to add something, add something to it, add something to it. And suppose this coil generate a B field using the right hand rule point to this side, and then this is decreasing, and then it tries to compensate it so that it will try to generate some B field in this direction, to overcome this decrease. So the EMF should be counterclockwise. So it should be counterclockwise. The E is counterclockwise. From another point of view, so actually here we have a coil like this. So this is the positive direction. And then we follow all the mathematics for the Faraday's law. So we have a negative sign here, and then it turns out to be a positive answer, because all these variables are positive. If we define the upper direction is the x direction, so that all of these values are positive, and this coil is moving to the positive x direction, which means that V is also positive. X is of course positive. Actually, we can just assume this one is the 0 point here. So the answer is positive, which means that the direction of the EMF follows the right hand rule, which is counterclockwise. So you can determine the direction of the EMF either way by the Lenz's law, and then you can just think of the physical meaning. Okay, we have an current here, and then generate a B field. So this one is moving away, and then the B field become weaker and weaker, so that the magnetic flux here is decreasing, so that it will generate some B field in this direction. And then in this case, the EMF should be counterclockwise, so that the induced B field is point to the positive x direction. Or in the other way, you just follow all the mathematics, and then it comes out to be a positive value. So this positive value tells you that the EMF should be counterclockwise, given that this is the positive x-axis, and then follow the right-hand rule.